If you want to measure the distance between two coffee cups on a desk, you just pull out a tape measure. In mathematics, this tool is called a metric. A metric is simply the formalized set of rules for a ruler. It says that distances must be positive numbers, the distance from A to B is the same as B to A, and measuring a straight line gives you the shortest path. Once you establish a metric, you can build what mathematicians call a topology. Think of a topology as a map that defines exactly which points sit close to each other, grouping them into local neighborhoods. Having a clear definition of closeness is the baseline rule that allows us to draw smooth, continuous, unbroken lines in mathematics. In the study of topology, the exact distance between points that are very far apart is often irrelevant. What matters most is what is happening in the immediate neighborhood. To reflect this, we can use a standard bounded metric. Imagine taking a ruler and erasing every number past 1. For objects closer than 1 unit, you measure exactly, say 0.4. For objects 2 or 2,000 units away, the ruler stops. It just reads 1, meaning far away. This concept is formalized here, in Munkres Topology. This equation defines the distance, d bar, as either the true measurement or exactly 1, whichever number is smaller. Capping our ruler this way allows us to keep local neighborhoods well defined, even when we start dealing with an endless list of coordinates. Let's leave the desk behind and move into infinite dimensions. Picture a vast control board with an endless row of dials stretching out of sight. Our challenge is to make a smooth, continuous adjustment across every single dial on this infinite board at the exact same time. One way to set the rules for this is the box topology. You can think of this method as a boss who demands absolute control over every variable. This approach draws a strict margin of error around every single infinite dial.
But when you move a master slider, a microscopic shift ripples down the line, eventually pushing a distant dial out of its box, triggering an error. Because even the smallest movement eventually breaks a rule somewhere down the line, we can't draw an unbroken path between two settings. In this system, smooth movement is impossible. To make the system work, we need the product topology. Think of this as a boss who knows how to prioritize. Instead of policing everything, we only place strict error boxes on a few dials. We ignore the rest. Because the remaining infinite dials have no strict boundaries, they can spin freely. When you adjust the master slider, no alarms trigger. By restricting the strict rules to a small, finite set, we finally gain the ability to make smooth, continuous connections across the whole board. By prioritizing a few dials and letting the others be, we ensure the system remains flexible enough to actually move. Checking every dial guarantees failure, while ignoring almost everything feels too loose. There is a middle ground between these two extremes. It is called the uniform topology. Instead of looking at individual dials, this method scans the entire infinite board. It finds the single largest error happening at any given moment and records it on a master gauge. However, if we used a normal ruler to measure this, a wild spin on just one distant dial could blow the measurement up to infinity, making the math fail again. To solve this, the uniform metric uses the d-bar symbol we saw earlier. It brings back the capped ruler from Act 1. Because this ruler caps out at 1, the maximum error across the infinite dials can never reach infinity. The measurement is always safely contained. The uniform topology succeeds because it uses that capped ruler to monitor an infinite number of variables at once. Changing how we measure solves the problem of infinity. When we face infinite dimensions, we have 3 choices: demand strict perfection for every variable, selectively prioritize what matters most, or cap the extremes so they don't overwhelm the system. In these mathematical spaces, demanding absolute, rigid control over an infinite set of variables makes it impossible to define smooth, continuous change. By choosing the right perspective, either by focusing on the most important dials or by capping our measurements, we can navigate the infinite smoothly and continuously.